What's going on, everyone? Let's talk about sigma notation. Okay, so in simple terms, sigma notation is just asking you to evaluate a function or a math problem, right, f of x, multiple times using a range of input variables or x values. Okay, once you complete those calculations for some given interval, you're just going to add up all those answers together, and it's going to give you a numerical answer typically. All right, and so this is what a sigma notation is going to look like generally. Okay, and so the sigma here represents a summation. So in here, you would say you're considering the summation, right, of some function f of x sub n, right, and we'll get to that sub n in a minute, over some interval from a to b. And so the important bit I want you to take from this form here is that this right here, the expression that you see right in front of the sigma, this is going to be your function that you're evaluating, okay? And then over here, the values that are under and over, right, your summation sign, A and B, this is going to determine the interval, right, over which you're making these calculations. And pictorially, right, like visually, what I mean by this is that if this is your curve, right, for your function f of x, A and B is going to be the interval over which you're making these calculations, right? So you're starting at A and you're ending at B, And so this is going to be the range over which you evaluate, all right? And so as a whole, what this means is you are going to evaluate your function, right, f of x, beginning at x is equal to a. So you're going to find the output for x is equal to a. You're going to calculate it for the next step over, and you're going to keep on calculating at every value of x, right, until you finally get to b, right? And this is going to be the last calculation you do, okay? And then x is equal to a, this is going to be the first input value that you calculate at. And so let's look at an example of this, and it should clear it right up. So let's look at this example, okay? So the summation, right, from n is equal to 0 to 3. So I want my interval to start at 0 to end at 3. And I want to evaluate this function, x squared, right, our parabola. And so based on this, what I'm asking you to do, right, is to evaluate the function, right? In this case, the function that we're considering is x squared, right? Our interval starts at 0, 0, and it ends at 3, okay? And so to calculate this, we're going to calculate our function at f evaluated at 0. We're going to add that to the same function, x squared evaluated at x is equal to 1, plus f evaluated at 2, and finally at f evaluated at 3, okay? And always remember that the first term, right, where you evaluate your function is going to be this value, and the last term, the last x value at which you evaluate your function is going to be this value, okay? And so in this case, all we have to do is simplify, right? And so let's evaluate x squared at x is equal to 0. So wherever you see an x, put a 0, so 0 squared, right? Plus, and then let me rewrite this in a different color so we don't get thrown off here, right? So we said this is 0 squared, plus evaluate at 1. So wherever you see an x, put a 1, 1 squared, plus evaluated at 2 squared, plus evaluated at 3, 3 squared. Okay, once we simplify, we're going to get 0 plus 1 plus 4 plus 9, and that's going to give us a whopping 14, right? And that's going to be your final answer. All right, so just to see if this kind of stuck, right? Let me give you an example, and then you take a second and try it. So the summation of n starting at, let's say 1, and then ending at 5, right? And let's consider the function n plus 2, all right? So go ahead and pause your video and see if you can evaluate this, and then come back and then we'll work on it together. Sweet. So let's see if our answers match, okay? So we said from above that the two numbers, right, the number under the sigma notation and the number over the sigma notation tell us our interval, right, over which we're going to evaluate this function. And so we know that our function in this case is going to be n plus 2, right, n plus 2. And I should switch this, sorry, because this is a function of n, not a function of x at this point. A function of n, okay? Because n is what we're going to plug in. And so our function is n plus 2. The first value in our interval is 1, so we're going to start there. We're going to end at 5. And now we're going to calculate every value in between. So this is asking you to calculate the function at 1, right? Add that to the function evaluated at 2, to the function of 3, the function at 4, and finally, the function at 5, okay? And so when you simplify this, evaluating this at n is equal to 1, right? So 1 plus 2 is 3. 2 plus 2 is 4. 3 plus 2 is 5. Plus 4 plus 2 is 6. 5 plus 2 is 7. And when you simplify further, this is 7, 12. Sorry, 7, 12, 18, 25. So this is going to be 25. Okay, and so this is going to be the final numeric answer for this sigma notation. Okay, so take a second and kind of comprehend it, and then after this, we're going to go the opposite direction. Okay, or the whichever way. So now that we know how to evaluate a sigma notation, right, when it's given to us in this way, now I'm going to give you a pattern of numbers or a collection of numbers, and you are going to find a pattern and try to put it into sigma notation, all right? So let me show you what I mean. So if I give you the collection of these numbers, all right? 1, 2, 3, and 4, okay? From this collection of numbers, your job is to, 1, right, find a pattern that will take you from the previous number to the next, to the next, to the next, okay? And then 2, you're going to generalize that pattern using sigma, right? Using sigma notation. Using, right, sigma notation. And it can be a function of anything, not just x, but I'm just putting that because we're familiar with f of x, okay? So pause the video and see if you can do this. All right, let's see if we found the same pattern, right? So you might notice that whenever you jump from the first number to the second number, or the second number to the third, and so on, all you're doing is adding 1, right? Same thing here. And so you know that the general pattern is going to be the previous number. Let's call the number n, right, as a variable. And as you progress, you're just going to take the previous number n and you're going to add 1 to it. Okay, this is the pattern. So in this case, this is your function, is n plus 1. This is your f of n. Okay. Now you need to determine over what interval, right, over what values of n only give you 1, 2, 3, and 4. Nothing else, just these 4 numbers. And so you're going to know that your interval has to start at 0, because 0 plus 1 gives you the first value, right, in this collection of numbers. And you know that this interval has to end at 3, because 3 plus 1 gives you the last number in this collection. So this is going to be your generalized sigma notation, right, for this collection of numbers. Sweet. So let's go to another example. So again, I'll give you the numbers and then you can take a second and see if you can find a pattern and generalize. Okay, so we'll go 9, 4, 1, 0, 1, 4, and 9. And for some folks, this might look familiar, and hopefully it does. Okay, so go ahead and give this a looky-loo and see if you can figure out the pattern and generalize that pattern using the sigma notation. Okay? Awesome. So by looking at these, it's a little more tricky than this first one, right? Because as you go from 9 to 4, right, if you take this approach, you subtract 5, but to get from 4 to 1, you only subtract 3, and to get from 1 to 0, right? So that's not the pattern. So you're going to look at these numbers now, and you're going to say, hey, what do I notice about each of these individual numbers, not the relationship between them as you progress, okay? So let's look at 9. 9 can be calculated as 3 squared, right? 4 can be calculated as 2 squared. 1 can be calculated as 1 squared, right? And same thing over here. So let's just write those back down over here. 2 squared, right? 3 squared. And then 0 can be calculated as 0 squared. So do we have a pattern from here that you can generalize into a sigma notation, right? So not necessarily yet, right? But notice that when you square a number, whether it's positive or negative to begin with, it always ends up being positive. And so, right, these values can actually be -3, -2, -1. And so now that you see this pattern, this looks like something you can generalize. Because as you go from -3 to -2 to -1, 0, 1, 2, 3, right? You're increasing this by 1, right? And all of these terms are being squared. And so in that case, you know that every number in this whole collection is being squared, right? That's the common relationship between them. So this is your function. Now you must figure out the interval. So n starting at, and we said that because each of these values only go up by 1 as you go from left to right, you can safely say it starts off at -3 and it ends at +3. Okay, and this is going to be your function, or your sigma notation, sorry, for this collection of numbers. And just in case it did look familiar and you didn't have your hands on it, that's actually this, our friendly parabola. Okay, so that's what that looked like. All right, and so let's work on two more. I'm going to give you this one. They might get harder, they might not. So here, let me give you this one. 1/4, 1. I'm going to put does not exist, or right, what we consider as blown up with a tip or infinity. 1 and 1/4. So go ahead and pause the video and see if you can't find the pattern in this collection of numbers, okay? And then try to generalize it into segment notation. Awesome. So, right, so it's getting a little hotter in the kitchen. So we went from adding 1 every time, then we went to, right, squaring our value of n that changes, right, over our interval. Now we have fractions, and in there we have a does not exist or infinity, or like a blown up function, right? And so let's start here. We know that in order, or one of the ways, sorry, for a function to blow up, right, in terms of calculus 1, it's going to be that you divide it by 0, okay? And so this can be rewritten or thought of, right, as 1 over 0, okay? And so since we have this one in fraction form and we have 1/4 in fraction form, let's put all of these in fraction form to make it easier on ourselves. So to see if we can catch something. So 1 over 4, 1 over 1. Let's call this 1 over 0. And then same thing over here, 1 over 4. Okay, so now let's consider this collection of numbers, okay? Because now you can actually compare apples to apples, all right? And so similarly, how, right, to go from here to here, you had to add 3/4, and to get to here, it's a little bit hazy, right? So that can't be a pattern in between numbers as you jump. So now let's look at the individual values to see, similar to what we did here, right? The numerators are all 1, so that's not the pattern, or that's not the direct pattern, right? But when you look at the bottom, okay, 4, right, can be found by squaring positive or negative 2. 1 can be found by squaring positive or negative 1, right? 0 is 0 squared, totally fine. And then same thing over here, right? Positive or negative 1, and then positive or negative 2. And so if you take these to be positive 1, positive 2, you take this to be 0, right? You take this to be negative 1 and negative 2, all these values squared, you basically have the inverse of what we just had above. Okay, so you're going to have 1 over the number squared, right? 1 over the number squared, 1 over the number squared, 1 over the number squared. So you're going to have 1 over n squared, right? This is your function. Now you must determine the interval. So here we said that, as you can see, negative 2 to negative 1, 0, 1, 2. This thing starts at negative 2. It's going to end at positive 2. Okay, so if you were able to get this, good job, good eye. Okay, and then last one, this one is going to be a little bit different, but we are going to toss in a little bit of fun. So let's do this one. The first one is going to be e to the cosine. Oh, it's getting pretty in here. 2x. Okay, the next one is going to be e to the 2 cosine 4x. The next one, e to the 3 cosine 6x. Last one, e to the 4 cosine 8x. Okay, pause the video, find a pattern, generalize it back into sigma notation. Okay, and then come back here and then we'll look at it. All right, so let's see if we got enough game to figure this out. So when you look at this, you get a little seasick. I'm just kidding. You're going to see that e to the stuff is a common thing, right? And so safe to say that's going to be in your function, right? So it's an exponential raised to the, and so let's start looking at the actual exponents here, okay? Because this is obviously where we're going to see our patterns. And so the first thing you should notice, or that you might notice in here, is that cosine of 2x, right, is the same thing as 1, right? That's definitely not a pen. 1 cosine of 2x, okay? This coefficient doesn't make a difference, but if you put it there, you can now compare across because they all look the same. So now you have this thing, right? 1 cosine of 2x, 2 cosine of 4x, 3 cosine of 6x, and 4 cosine of 8x. Now let's look at these. The next pattern you're going to see is that the term inside of each of these cosines is going to be twice or double the coefficient, right? Because 2 is twice as large as 1. 4 is 2 times the 2. 6 is 2 times the 3. 8 is 2 times the 4. And so now you know that inside of cosine, right, is always going to be 2 times some number, right? Call it n, and then x, because x is in all of these. So it's safe to say that's in there. Okay? So the inside is 2 times some value n, and we said that it's 2 times the number that's the coefficient here. So this is just n, right? So now we have our function e to the n cosine of 2nx. Okay, so now let's figure out our interval. Based on this, right, if you're just looking at your coefficients, 1, 2, 3, 4, this thing is starting off at 1. It's ending at 4. Okay, and this is going to be your sigma notation for this pattern. All right, so if you got this, you're definitely on the right track. If not, you're totally fine. Just go back and look and see what you need. All right, so this was sigma notation going frontwards and backwards, please. All right, if you have any questions or comments, feel free to leave them below and I'll get back to you as soon as possible.